Okay, here's warm-up number 24. I've got two binomials here that I'm going to multiply together in order to simplify this. So these are complex numbers because they have real and imaginary parts, but I'm going to just start off by pretending, what if those were just x's? What would I do if I had 2x and negative 5x in there? Well, I'd FOIL this, right? So that's what I'm going to do. So first, outer, inner, last. First, 3 times 4 is 12. Outer, 3 times negative 5i would be negative 15i. Inner, 2i times 4 is 8i. And last, 2i times negative 5i would be negative 10i squared. Okay? All right. Then I'm going to start combining like terms. I've got these like terms in the middle here. That would give me negative 7i. Okay. And then at first glance it might seem like there are no more like terms, but there actually are, because I squared, I can do something with that. If you remember, I equals the square root of negative 1. That means I squared is going to be the square root of negative 1 squared, and those undo each other, so that means I squared is going to equal negative 1. So if you just remember I squared equals negative 1, anytime you see an I squared, you can replace that with negative 1. So then I've got, this is going to be negative 10 times negative 1. That's positive 10. And now I do have some like terms, okay? And usually we'll put the real parts out front. So when I combine these into 22, I'm going to write the 22 first. It wouldn't be wrong if you said negative 7i plus 22, but this is how it's usually written when we have a complex number, okay? All right, moving on to the next one. Here I've got two trinomials that I'm multiplying together. So I can't use FOIL here because they're not binomials. I'm going to use what I call the multiplication chart method. So I'm going to take these three terms and I'm going to write them vertically like this. Okay, and I'm going to put those on the left edge of a box. Okay, and then on the top of the box I'm going to use these three terms. And I usually get asked, or by somebody, why didn't I write the plus there? But, well, because I'm just writing what the three terms are, just like I did over here. I didn't write x squared plus 3x, right? I'm just writing the values of those three terms. It doesn't really matter if you put in the plus, but that's why I didn't put it in. And then I'm just going to treat this like a good old-fashioned multiplication chart. So in the top left corner, I'm going to do x squared times 2x squared. That's going to give me 2x to the fourth, right? X squared times x squared is x to the fourth. And then x squared times negative x would be negative x to the third. X squared times 3 is 3x squared. Okay, moving on to the next row. 2x squared times 3x is 6x to the third. 3x times negative x would be negative 3x squared. And then 3x times 3 is 9x. And then negative 1 times 2x is negative 2x squared. Negative 1 times negative x. Negative 1 times 3. Okay, so I've got that chart filled out. And now if I add together the contents of all the boxes, that is going to be the product here. Okay, so let's start doing that. And I'm going to combine these like terms as I go. Okay, so 2x to the fourth is the highest degree term in there. So I'm going to write that first. And next I'm going to look for the cubic terms, the third degree terms. And there they are. There's both of them, okay? So when I combine these, 6x to the third minus x to the third, that would give me 5x to the third, okay? And then my squared terms, those are also lined up on a diagonal. And that happens a lot on these problems. Not always, but it happens quite often. So let's see. This would be negative 5x squared plus 3x squared is going to give me negative 2x squared when I combine all of those. Okay, here's my x to the first term, so that would give me 10x. And then last, I've got negative 3. And no more like terms, so this is finished. Okay, nice thing about this method, it doesn't matter how many terms it has. You could actually do this with binomials as well. But even if they both had 17 terms, then you could still use the multiplication chart method. Okay. All right. Next up, this says expand using Pascal's triangle. I could, do 3x plus 2 times 3x plus 2 times 3x plus 2 times 3x plus 2. It would take me a little while, not that long, but it would take me a lot longer than it would to do this with Pascal's triangle, okay? So here's Pascal's triangle. The top row, you might think that would be called row 1, but it's not. It's row 0, okay? And then this is row 1, row 2, and so forth. Okay, so the first thing I want to do when I'm setting this up, I'm going to use just one of those rows. In this case, I'm using row 4 because it's a 4th degree binomial, okay? So I'm only going to be using this part of Pascal's triangle here, okay? Now I'm going to set up another chart. I've got a little triangle symbol and then A and B, okay? And I'll explain what the A and the B are later. But let's start with the triangle. Those are just going to be the coefficients from row 4. So I'm going to write them in here. I'll space them out a little bit to give myself room in the other rows. Okay. And then I'm setting up a chart like this. Okay. The A and the B are going to refer to the terms of the binomial. So the first term is going to be, in this case, is going to be 3x. The second term, my B term, is going to be 2. Okay? So what I'm going to do in the A row, first I'm just going to put 3x all the way across in every space there. Okay? And then for the B row, I'm going to put 2 all the way across. Okay? Now, the A and the B rows, I'm going to be raising them to different exponents. And it doesn't really matter with the b's because it's just a number, but with the 3x row, since there's a number and a variable, I'm going to put all of these in parentheses because raising this whole thing to the second power is not the same as just raising the x to the power. So, in other words, this is not the same as this because this would actually be 9x squared, right? Because 3x times 3x is 9x squared. Okay, so I'm putting those all in parentheses. All right, and then what I'm going to do, since this is the 4th row on this first piece, I'm going to raise that to the 4th power, okay? And then I'm just going to go down from there. So if this is 4, I'm just working my way down, 4, 3, 2, 1, and you should end up on 0. If you didn't end up on 0, you probably used the wrong row from Pascal's triangle, okay? So 4, 3, 2, 1, 0. And then on the next row, I'm going to start at 0 and work my way up. 0, 1, 2, 3, 4, like that. Okay? So that's kind of just a pattern that you got to memorize. Now what this is going to do, if I take the columns that I've set up, like this first column here, if I multiply these 3 things together, it's going to give me the first term of my polynomial after I've done all the multiplication, okay? So this first term, I've got 1, and then 3x to the 4th. I'm going to simplify this as I go, okay? 3x to the 4th. Don't just write 3x to the 4th without parentheses because you're going to raise the 3 to the 4th and the x to the 4th. So 3 to the 4th, I mean, it's just going to be 9 times 9, right? Because 3 squared times 3 squared. But there's a calculator, okay? So I've got 81 x to the 4th is equivalent to this, okay? Anything raised to the 0th power equals 1. So there is going to be, and that's just going to end up being 81x to the 4th, right? But that's going to represent the first term of my polynomial. The second term is going to come from the second column. So I'll do the same kind of thing. I've got 4. Okay, 3 to the 3rd is 27. 3 times 3 times 3, so 27x to the 3rd, if I write that without parentheses. 2 to the 1st is just 2. Okay, and I'll multiply that all together later. But I'm going to just kind of work my way down these different columns. And a lot of times I don't leave myself enough space on these, but let's see if I can get through it here. So I've got 6. 3x times 3x would be 9x squared. 2 to the 2nd is 4. Oh, got to write a little smaller here. And then next one, I've got 4 times 3x. Okay, and 2 to the 3rd is not 6, right? 2 times 2 times 2 is 8. And my last one, I've got 1 times 3. Anything to the 0th power equals 1. 2 to the 4th, well, that would be 2 to the 2nd times 2 to the 2nd. So 4 times 4 is 16. 2 to the 4th then is 16. Barely got it in there. That says 1 times 1 times 16. Okay? Then I'll just start simplifying. I can see this first one's pretty easy. 81x fourth, because we're just multiplying by 1 twice. Okay? 4 times 27 times 2 is going to come out to 216. Okay, that's 4 times 27 times 2, and then I got x to the third. Okay? 6 times 9 times 4 is also 216. And then I've got an x squared. Okay? 4 times 3 times 8 is going to come out to 96. And 1 times 1 times 16 is 16. Okay? And yeah, it takes a little while, and there's a lot of room for error using Pascal's triangle, but it's actually a lot quicker than multiplying it out by hand, especially if we had something like 3x plus 2, the quantity 3x plus 2 raised to the 7th, because that just means the chart would be a little bit bigger. But if you did the multiplying by hand, it would take a really long time once you get some higher exponents there. Okay, and that's it for today. See you next time.